Welcome back. In the last video we looked at how to find a stationary point on a curve. Somewhere where the gradient is 0, the graph is flat, where dy by dx equals 0. And we said then that you can find that x value and turn it into a coordinate. Now, knowing that on its own is not particularly useful. So knowing where a stationary point is great, but it's even better if you know whether it's a maximum, a minimum, or a saddle point, and we discussed these in the last video. In fact, I just copy and pasted that from the last video. So a local minimum is where the graph in a sort of small area that you're looking at reaches its lowest point before coming back up. A local maximum is when you look at a certain portion of a graph and it's the highest point before coming back down. And then we had a point of inflection, a saddle point, where it flattened off but then kept increasing, and we said that it could go the other way around. It could be coming down, go flat, and then continue to go down, which is quite common for x cubed. Now, you don't got to worry so much about the third one, the saddle point, in additional maths. It's more important that you know about local minimums and local maximums. So how do you find whether it's a local minimum or local maximum? Well, it's all to do with the rate of change of gradient itself. Okay, so if we have a look at these graphs, this is like a typical x squared shape, I suppose, isn't it? It comes down, it reaches minimum, goes back up again. There's only one stationary point. So here, the gradient is negative. It's very steep. Okay, for instance, it might have a gradient of -10. As you come further down the graph, it's still got a negative gradient. The graph is still going down, but not as steep. So still negative, but maybe -5. By the time you get to here, it's still negative, but maybe only -2. And then you get here, where your gradient is 0. The graph is flat, dy by dx is 0. After that point then, the graph starts to have a positive gradient. Not by much. Maybe it starts at a gradient of 3, then increases to maybe a gradient of 8, and then maybe to a gradient of 12. So it was very negative, not as negative, 0, and then went positive. So the gradient itself is increasing. Okay, so the gradient on this one is increasing. When it's the other way around, upside down, and what we're looking at is a local maximum, if you start on the left, here this graph is positive and very steep. Here the gradient is still positive, the graph is still going up, but not as steep. Here the graph is still positive, but not by much at all. Okay, very small gradient, especially compared to here. Then we've got where our gradient is 0, our stationary point, and then the gradient turns negative slowly at first, but then that gradient is increasing or decreasing all the time because it's getting more and more negative as the graph gets steeper. So on this one, the gradient is decreasing. It was high and positive. It comes all the way down to being 0 and keeps going down till we end up with a negative gradient. The graph turns around and heads down when it was heading up. So how do you find that without having to actually look at lots of different points on a graph? Well, gradient is dy by dx. If you want to find the rate of change of gradient, you have to differentiate again. So you've already found dy by dx. Well, now you have to find what's called d squared y by dx squared, the second derivative. So gradient is how the graph changes, but now we're looking at how the gradient is changing. Okay, so we're differentiating what we've already differentiated. It's called the second derivative, and it's written as d squared y by dx squared. If you were working in terms of f of x, then when you differentiate once, remember we said that was f dash of x, this is in a video a long time ago, Well, now if you differentiate twice, that would be f double dash. And what we say then, if I can stretch this down a little bit, if d squared y by dx squared is positive, so that's like this, increasing, the gradient is increasing, it was negative, then it was 0, then it was positive, so the gradient is increasing. That means you have found a local minimum, which seems back to front because positive means you've got a minimum. If d squared y by dx squared is negative, and what I mean is you'll be subbing in values of x into this d squared y by dx squared. If that comes out negative, what you found is a local maximum. So it's opposite to maybe what common sense would tell you. D squared y by dx squared is negative, that's a maximum point on a graph. If d squared y by dx squared is positive, you found a minimum point on a graph. And the best way to sort of go through this now is to actually do an example from scratch, finding the stationary points and then finding their nature. Remember, you don't have to worry about saddle points at additional. That comes later on in A level. It's a bit trickier to prove whether it's going up, going down, or what it's doing. Here's a question then. Find and determine the nature of the stationary points for this equation, y equals x cubed minus 12x plus 3. So you know from the last video how to find the stationary points. So if you pause the video first and just find the stationary points and give them as a coordinate to start with. When you're ready, press play. Right, dy by dx then is 3x squared minus 12. The x goes, the plus 3 goes. Then we've got to find where that is 0, because that's how you find stationary points. You put dy by dx equals 0. This is not a sort of a full quadratic, so it's not very difficult to solve. 3x squared equals 12, so x squared equals 4. Remember, you have two solutions when you square root, one positive, one negative. So x is either 2 or x is minus 2. To get those as coordinates, I've got to substitute back in to my original function equation. So when x is 2, we get 2 cubed minus 12 lots of 2 plus 3. So that's 8. Take away 24, that's minus 16. Plus 3 is minus 13. And so our first stationary point is 2 minus 13. When x is minus 2, so we have minus 2 cubed, minus 12 lots of minus 2 plus 3. Be careful with your signs here. So that's minus 8 for minus 2 cubed, plus 24. So that's positive 16 plus another 3 is 19. And so we've got minus 2, 19. Now it might help to sort of sketch this, what we've got so far. So here's the set of axes. I'm not going to put a scale on, but I know I've got a stationary point at 2 minus 13, so there. And I've got another stationary point at minus 2, 19, which I'll put up here. Minus 2, 19. I also know that the original graph has a y-intercept of 3, so I could even mark that on there. Now I need to know whether these are minimums or maximums. I mean, I guess it's pretty obvious sketching it out. How can this be a minimum here if I've got to end up down there? So chances are, I don't know for sure yet until I do the second differential, but I would guess that this graph must do something like that to join the dots up. But to prove whether they're maximums or minimums now, I have to do the second derivative. Now then, remember we've already got that dy by dx is 3x squared minus 12. So I differentiate that again. So d squared y by dx squared. So this will go to 6x. and the minus 12, because it's just a number, is gone. And you'll find that quite often this second derivative is quite nice, because by the time you've differentiated twice, most of your powers will have gone and you'll be left with something reasonably straightforward. So what do we do with this? Well, we take our two stationary points, 2 and minus 2. We've already substituted them once to complete the coordinate. Now we're going to substitute them again to determine the nature of the stationary points. We're going to substitute them into our second derivative. So when x equals 2, d squared y by dx squared equals 6 lots of 2. Remember, it's 6x, so 6 2's are 12. 12 is positive, so this is a local minimum. So when x is 2, this is a minimum. And so I'll sort of just put in a little bit of minimum. We can join it all up later. When x equals minus 2, d squared y by dx squared, this time is 6 lots of minus 2. Remember, I'm using this equation in the box here, our second derivative. That's minus 12. When it comes out as negative, you found a local maximum. Remember, they're sort of back to front. And so I've now confirmed what I already thought, that this coordinate minus 219 is a maximum, and this coordinate 2 minus 13 is a minimum. And so what you can actually do now is sort of roughly sketch, so that's going to keep going forever. There's no more stationary points, because if there were, I would have found them here. So this graph now goes up forever, and this graph on this side goes down forever, and you can get a pretty accurate sketch. And we proved algebraically that we had a maximum on the left and a minimum on the right. Let's do another one. So the equation looks a bit nastier, but the steps are the same. We're going to differentiate to find the stationary points, get values for x, values, we'll wait and see how many there are. You put those values back into that equation to get them as coordinates. Then we're going to differentiate again, so we can substitute our x values into the second derivative, and that will tell us whether they're maximums or minimum points. Let's have a go. Feel free to pause the video and have a go yourselves if you're confident enough. So dy by dx is 6x squared. I should have had a squared on, by the way, sorry there. Minus, so that's going to change that to minus 30x plus 24, and the 8 disappears off the end. And now I've got to put that equal to 0. So 6x squared minus 30x plus 24 equals 0. Now you could factorise with those numbers, but those numbers are massive. Now I notice actually that all of these are multiples of 6. So to make this a bit easier, I'm going to divide everything by 6. That leaves me with x squared minus 5x plus 4 equals 0, because now I've only got to factorise what's in here. So what multiplies to make 4 and adds to make minus 5, that's minus 1 and minus 4, and because there's nothing here, I can go straight to brackets. Look, minus 1, minus 4. Don't worry about the 6 outside, because that's nothing to do with x. So to find our solutions, just go to your brackets and solve them for 0. So if x minus 1 is 0, then x equals 1. And if x minus 4 equals 0, then x equals 4. You would have got the same answers if you'd factorised this. It's just the numbers wouldn't have been as nice. You would have had to find two numbers that multiply to make 144 and add to make minus 30. That's going to take ages. So what I did, I noticed everything could be divided by 6. So I divided it through by 6 to make my factorising easier, and it gives the same solutions anyway. Okay, now you've got to get those as coordinates. So when x equals 1, I'm subbing back into this at the minute. Now I haven't got much room, so when x equals 1, y equals 2 lots of 1 cubed minus 15 lots of 1 squared plus 24 lots of 1 plus 8. You'll have to trust me on this. That comes out as 19. If you don't trust me, work it out, but it's 19. So our first stationary point is 1, 19. And then when x equals 4, so 2 lots of 4 cubed minus 15 lots of 4 squared plus 24 lots of 4 plus 8. Now that comes out as minus 8. So our second stationary point is 4, minus 8. So if you wanted to sketch this before we go any further, we've got a stationary point at 119, so maybe up there. Nothing wrong with sketching if it helps. And we've got 4 minus 8, which is down here. And also we've got our y-intercept is 8, so we can even put that on, which would be roughly there. I'm not putting a scale on, this is just rough positions. And then we find whether these are maximums or minimums, and the sketch helps because you can see it goes up through there and then comes back down. So I would assume that this is a maximum and this is a minimum, but we still have to prove it. So starting with dy by dx, which was 6x squared minus 30x plus 24. Now we're going to differentiate again. So d squared y by dx squared, that comes out as 12x minus 30, which is not bad for substituting into. And the numbers we're subbing in are these x values from the first part of the question. Okay, it's this and it's this. So we say when x equals 1, d squared y by dx squared, our second derivative, is 12 lots of 1 minus 30, which is minus 18. If it's negative, it's a maximum. So when x equals 1, this is a maximum. When x equals 4, d squared y by dx squared is 12 lots of 4 take away 30. That comes out as positive 18. Positive means it's a minimum. So I'm some issue writing today. So there's a minimum, and what you can do then on your sketch, like you can fill in the gaps. So it goes up through 8, gets to a maximum at 1,19, comes back down, gets to a minimum at 4 minus 8, then it turns, starts going back up and never comes back down again. And I know that's true because if it turned and came back down again, there would have been a third solution here for some bigger value of x. So I know that once it starts going up here, it never comes back down, and when it goes down here, it never comes back up, because we proved here that there were only two stationary points and we've got them on our graph.